Okay, so in the previous video on circular motion at constant speed, we had shown that the object has an acceleration that is always toward the center. So here is the red acceleration vector. When the object is here, its acceleration is that way. When the object is here, its acceleration is that way. When it's here, its acceleration is that way, and so on. Let's make a few more. Acceleration vectors, sort of in between these positions. So this is red acceleration. Now let's focus on the velocity equation, right? So we take the derivative of the position, which is parameterized using r and theta in this way, and the velocity equation looks like this. The magnitude of the velocity is r d theta by dt. That's a constant at every point, but let's see the direction. So when the object is here, theta is 0, sine of 0 is 0, cosine of 0 is 1, and so we have a j hat. And so let's draw a blue velocity vector here, which is straight up. When the object is here, theta is 90 degrees. Sine of 90 is 1. We have a minus sign. Cosine of 90 is 0. This goes away. We have a minus I hat. Therefore, the direction of the velocity there must be to the left. When we're here, we have 180 degrees. Sine of 180 is 0. Cosine of 180 is minus 1. So we have a negative j hat. So we're pointing that way. When the object is here, unsurprisingly, it'll be an I hat. This will have to go away. The cosine of 270 or minus 90 is 0. The sine of minus 90 is minus 1. We have a minus sign here. We get a positive 1, and that gives us an I hat. And so the velocity points tangent to the circle, unsurprisingly. And so here it would be that way. Here it would be that way, and so on. The thing to notice is that the velocity is always perpendicular to the acceleration. And this is in contrast to where we started the course, where we said that if there's an acceleration, let's say a star, right, by definition, that's dv by dt, right? So an object accelerates with some, say, constant acceleration a star. What we get is that its velocity is equal to some initial value plus a star t. And this equation, this kinematic equation that we derived from the definition of acceleration, tells us that the v value changes with time if the acceleration is not 0. And yet that seems to be not occurring here. We have a non-zero acceleration, but the value of v is always the same. It's r d theta by dt. It's not changing. So this is a very special kind of motion. It's motion where the acceleration is perpendicular to the velocity, and those are the conditions that allow for the velocity to change with time because there is an acceleration, but only in terms of direction, not in terms of magnitude. And we'll go deeper with this, but it's a little bit like saying an object is moving with velocity v that way, and if you want to speed it up, you will pull it in that direction. If you want to slow it down, you will pull it, so here's the object, you'll pull it in that direction. If you want to neither speed it up nor slow it down, but change its direction, you would pull it that way or that way. Okay, so those are the directions of the acceleration. And acceleration will be related to force when we get there, and then we'll derive the notion of work, and this kind of motion will result from forces that do 0 work.